Well, hi there. We're going to have another look now at complex regions or loci, part 2. And we've got some more circles for you, okay? Circles, 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 everywhere circles. Because circles are a big part of this, and there are other ways of expressing circles than what we've so far been used to. Okay, so fasten your seatbelts, get a nice cup of tea, and we'll blast off into the land of the circle, okay? First cab off the rank, we've got a funny looking beast here. We're saying that the argument of z is greater than or equal to pi on 3, but at the same time it has to be less than 2/3 of pi. Okay, that's argument, that's the angles. And at the same time, and we're saying that the modulus of z, that is the distance of z from the origin, has to be greater than or equal to 2, and at the same time has to be less than 4. Yes, I think we can do that. No problem. Let's do the circle bit first. Okay, now you know what that looks like by now, don't you? I think you do. It looks like, wait for it, here it comes, there. Yes, but it doesn't look like that. It's less than 4, so therefore we're going to dot that circle, and therefore we're going to put the shaded region inside. There it is. That's where the length of the line from the origin out to wherever it goes has to be less than 4 units. So it's anywhere inside that circle but not on the boundary where it equals 4. Yes? Now, we're going to look at this one now where, okay, we're looking at where the modulus of z, or the distance of z from the origin, is greater than or equal to 2. Well, that would be anywhere outside a circle of radius 2 with the centre at the origin, wouldn't it? I think so. See, you're getting really good at this now. I can tell. I can catch the vibes. Well, I think you are anyway. So there it goes. That's greater than... Yeah, it's everywhere outside that circle which has a radius of 2. The length of the line from the origin to any point outside that circle will be greater than 2. Yes? And that's what we're supposed to be. And we also can have it on the line because it can equal 2. Okay, so I've done a hard continuous line there for the boundary of the circle. Good? Now, therefore, if you want the bit that does both at the same time, can you imagine what that would look like? Yes, I think you can. It's going to be, that's the outside bit, and what about the inside bit? Yeah, there it is, got it. So it's anywhere in this donut region from there, including that boundary, inside here, inside Argand cyberspace in here, right? But not getting to the very outside edge of the circle where the radius is 4, and certainly not outside it. That's where both of those constraints are applying at once, okay? It's outside of one but inside of the other, if you know what I mean. Good. Now, okay, so let's do the angle bit now. We're doing where the argument of z is got to be greater than or equal to pi on 3, but at the same time it has to be less than 2 pi on 3. I think I know what this is going to look like. I think you do too. We just have to be careful with the dotted lines and the continuous lines because that's where it gets all very messy. Okay? So here we go again. We're drawing this diagram. We're dotting the line of the outer circle, and here comes the inner circle with a continuous line, and there's where I've drawn the angle. That's pi on 3 there, right? That angle's pi on 3. This angle in here from the negative x-axis up to there is pi on 3, and we've sandwiched our little region in here. It neatly, snugly sits in there. How beautiful it is. So that's everything. Every constraint we've done. And we've got continuous lines here in honour of the continuous line on this circle. We've got a dotted line there in honour of the dotted line on this circle. We've got a continuous line on here in honour of the fact that the angle can be pi on 3 and can be greater than that up until the point where it has to be less than 2 pi on 3. Now, is that right? Let's do a final check. Yes, I think it is. I think it is, and I think we've done it. Yes? Good. Okay. Do I have permission to go on? Yes, I do. Don't say that. Yes, I do. So, find the Cartesian equation of and sketch the following subset of this thing. Now look, guys and gals, I need you to recognise, I don't really need you to solve this. This doesn't come up in the exams, but I needed you to recognise the form of this. If this number here is a 1, what have you got? Yes, you've got the perpendicular bisector of the line joining where x is 2 and x is 4. But if this number here is not a 1, I need you to understand very clearly, and I'm going to do it for you to prove it, but not for you to have to regurgitate the actual process, just for you to recognise that it is a circle. Oh, shock horror, is it? Yes, it is a circle. Any number other than a 1 is a circle, right? I'll do it algebraically and I'll do it geometrically for you as well. Okay? Now this, yes, when the coefficient is greater than 1, the locus is a circle, and it's not geometrically intuitive at all, guys. It ain't. So, pardon my English, here's the algebraic method coming up, right? And I'll prove it to you. You watch this. Okay, now this is the tried and true technique that we're all used to doing. It's creating a bit of a yawn now because we're so used to it. Change the z into x plus iy, and away you go. Yes, yes. And now gather the ducklings together, the reals and the imaginaries together, and go for it, okay? There we get that, and now we're going to Pythagorate it, and it comes to that. Now, if we square both sides, please remember to square the 2 as well as everything else, because students forget. There it goes. Now, okay, so I think we've got to multiply that right-hand side out. It's a bit of a mess. I've also multiplied the left-hand side out at the same time, and goodness, let's get rid of that bracket on the right-hand side before we can really do much. There it goes. Yes, 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 yes. Now, at any time, I give you permission to pause the video and try it for yourself, because you are getting good at this now, and you are starting to, you know, be able to fly on your own, okay, as it were. So, what are we going to cancel out? Yeah, 16 from both sides, and on the rest of it I think we have to manage. Yes, that looks good to me. Now, let's just turn it around so we've got pluses instead of minuses on the x squared and y squared terms. Good. And I'm going to have to complete the square because I've got a middle x term, which is a source of great annoyance, so I'm going to have to complete the square to turn that into a linear factor squared. Yeah, you don't have to do that with a y though, there's no middle y term. So 8 over 3x, yeah, you have to take that 3 there out of the brackets, that's what you have to do. And it looks like I'm looking for, half of that is 4 over 3, so if you square that you'd be 16 over 9, plus 16 over 9 minus 16 over 9 is what's got to go in there on the next line. Good. Yeah, good, good, good. Now, I've got to get this beastie out of here because he's got nothing to do with the completion of the square. He's just the dross. So, okay, this is the trinomial I want for completion of the square, which is going to be x squared minus 4 over 3 all squared. Oh, I've left it as it is like that. Now, when I take this term out of the bracket, please remember to multiply it by 3. Okay, so it's not going to be minus 16 over 9, it's going to be minus 16 over 3 for you and me. Fills us with glee. Yes, it does. Now, let's do the next line. Hello, Mr. Snail. How are you today? He can only slither. He doesn't answer. And if he did answer, you'd be deeply worried about me. That's for sure. Now, right, so x minus 4 over 3, yeah, all squared 3 times it. Yes, yes, yes. See, very close to our circle now, which we can recognise. I've got to divide both sides by 3 for you and me. There it goes. Okay, so what have we got, guys? We've got a circle. Centre is 4 over 3 and 0, and radius is 4 over 3. That's what it is. See, I told you it was a circle. It's definitely a circle, all right. So that's what it is. So please just recognise that if you've got a coefficient out here that isn't a 1, you've got yourself a circle, right? Good. Thanks, Mr. Box. Now, yes, this is the bit that's telling you that you don't really have to know how to do this, you just have to recognise. So the emphasis in the exam is more on the recognising the shape of this locus type, where we've got z minus a is n times z minus b, where n is greater than 1. Okay, I'll go as far as to say they never come up for analysis, but they do very, very seldom, but be prepared, as the Boy Scouts say, be prepared, seldom come up as a kind of a thing in a multiple choice question where you might need to recognise that that was a circle in a multiple choice question, okay? That's why I'm doing it, so it'll have an impact on you so that you'll recognise it, okay? Now, just continuing on with this, I think we're going to do the, oh yes, we're going to do the geometric way in a minute. So that's saying the distance of z from the point where x is 4 is twice the distance from where x equals 2. Now I need to emphasize that because that's important. The geometrical significance means it's further from 4 than it is from 2. It's twice as far always from 4 as it is from 2. Do you get that? It sometimes helps to write that out in English so that you can actually get it from rather than just looking at the maths and getting things round the wrong way. Yeah? Students can do that, and so can I if you don't write them out properly and get used to them. So here's the geometric method. Here we go. Now, again, this is for the sake of completeness and comprehension only, just to have an impact on you so that you'll be aware that these guys are circles, right? Now, let's draw it out. We've got, what have we got? Got our nice little argand. Okay, there it is. Now we've got the points. They're marked. There's where x is 2, and that's where x is 4. Okay. Now let's go with this. What I'm saying to you is that the circumference of the circle will cut the x-axis twice. Okay. The circumference of the circle will cut the x-axis twice. Once internally between 2 and 4. So once in here, and it'll be closer to 2 than it is to 4 because of this constraint up here. It's going to be twice as far from 4 as it is from 2, okay? And it's also going to cut it once internal. Did I say, yeah, I'd already said internally, and once externally outside the line joining 4 and 2. And the external one will have to be, in this case, over this side, where it's closer to 2 than it is to 4, okay, because it's twice as far from 4 as it is to 2, okay? Yeah, so that's where students get mucked up. They look at this 2 and they think, oh, that means it's twice as far from 2. No, that's not what it reads. It says the distance from 4 is twice as far as it is from 2, okay? So this is the distance that's twice as far, right? If you're getting what I'm trying to say, I hope so. So therefore, yeah, so the external division, the external point of where the circumference hits the x-axis is going to be over this side and not over that side, if you know what I mean. Okay, and the other thing is that the centre of this circle will be on the x-axis because the line joining x is 2 to x is 4 is, okay? And that's just the way it works out. All right, now, here we go. Let Z1 be the point of the internal division between 2 and 4, and we're going to let Z2 be the point on the circumference outside the line joining 2 and 4, which is going to be over here somewhere, okay? All right, let's go. Now, we do this to find Z1. We use simple ratios. We use a number line. It goes like that. Okay, so I've drawn, yeah, the ratio of the lengths are going to be in the ratio 1:2. So Z is going to be twice as far from 4 as it is from 2. So therefore I've drawn it in that kind of spirit. All right, now let's use some simple ratios. So I'm saying that the Z1 minus 2 over 4 minus Z1, and I've done that so that I get positive results. Okay, Z1 is bigger than 2, so Z1 minus 2 gets me a positive result, and 4 minus Z1 gets me a positive result, because I'm only interested in the distances, not the pluses or the minuses here, just the distances. So I'm angling to get positive results out of the numerator and the denominator. Otherwise I'll get myself messed up. Equals 1 is to 2, or 1 over 2. So cross multiplying, I'll get 2Z1 minus 4 equals 4 minus Z1, and we're going to solve that for Z1, and we'll see what we see. Therefore Z1 will be, what will it be? It'll be 8 over 3, which is, that's 2 2/3, and that is closer to 2 than it is to 4, because the midpoint would be 3, and that's 2 2/3. Okay, it's a little bit closer, but it's still closer to 2 than it is to 4. Okay, now we're going to find Z2 in exactly the same manner, but we draw a diagram first so we can see what we're doing. Now you see how I've drawn this Z2 over on the left, otherwise we won't get the right answer, okay? It's over on the left from our geometric intuitive understanding of what's going on here. So the ratio of the lengths that I've shown you are 2, the top one's 2, the bottom one's to 1, so 2 is to 1. So, okay, so how do we write that out, okay? what we say is therefore 4 minus Z2, which is the large length, over 2 minus Z2, which is the smaller length, is 2 over 1, and therefore we say 4 minus Z2 cross multiplying, equals 2 times 2 minus Z2, which is 4 minus 2Z2. Goodness, Z2's everywhere. Now we're going to solve this, aren't we? And we're going to get therefore Z2 equals 0. Goodness gracious me. So that means that this point of intersection on the circumference here, intersects right on the origin. Okay, right on the origin. So this means, ladies and gentlemen, we have now 2 points on the circumference which are diametrically apart, because the centre is going to go through, is going to be on the x-axis somewhere. Okay, so that really we've basically just about cracked the case. Okay, so therefore we're saying that Z1 is 8 over 3, or 2 2/3, which is in here, a little bit closer to 2 than it is to 4. Yeah, actually it's a ratio of 2:1, like I promised, and Z2 is here at the origin. So therefore we automatically can work out the diameter now. We can work out the diameter because they're points diametrically opposite each other. Therefore, the length of the diameter is going to be 8 over 3 minus 0, which is going to be 8 over 3 for you and me, and the centre, the radius therefore has to be 4 over 3, and the centre is basically going to be the average of those two extreme points on the circumference. They were 8 over 3, and this one here is 0. So the average of those 2 points is going to be the centre point, which is going to be 4 over 3, right? So that gets us exactly the same result as what we got before. Shock horror, incredible. There it is, Mr. Box. Now how did you like that? I reckon it's pretty groovy, very groovy. But that's it. Now yes, Mr. Computer, don't get into a lather. You don't need to learn this for the exams. I'm just showing you that this kind of thing is a circle, okay? So what have you got to recognise? That if this coefficient here is not a 1, if it's anything else, you've got yourself a circle, guys, okay? But if it is a 1, you've got yourself a straight line, which is a perpendicular bisector of the line joining each of these 2 points, which we learnt last time, okay? Alright, so now, other circles. Let's have a look at these beasties that you've got to learn to recognise, okay? Right. If z equals x plus iy, which we know it is, and c is another point which is a plus ib, another complex number, find the Cartesian equation for each of the following subsets of the complex plane. Okay, what do we got? Z times z bar equals r squared. That's a circle. You've got to recognise these after a while. This is a circle, definitely. Centre is that's got a centre at the origin, and it's got a radius of r. But you'll see that in a moment. Now this beastie is much more difficult to see, but it's basically the very close cousin of this one, similar in form, except that we're offset by this C here, which turns out to be the centre of the circle, okay? I'll show you that in a moment too, but you must be able to recognise this. This came out in a special report that the authorities published about complex regions, and then they up and put it in the exam that same year, and it comes up periodically from time to time, so you've got to know it. You must know it. This one here, I don't know why I even put it in. It's just that obvious. That's a circle. Yes. So let's do each of the 3 of them. Then we're going to do an analysis problem. Oh, goodness. Heavens to Murgatroyd. Yes, that's all right. It's a good one too. So that's what's that saying. That's saying x plus iy, which is z, times x minus iy, which is z bar, equals r squared. And that, if we multiply them out, we'll get, being a difference of 2 squares, x squared minus I squared y squared, which is just x squared plus y squared, seeing that minus I squared is plus 1. We get x squared plus y squared equals r squared, which you can see is a circle any old day of the week. Okay, so can you remember, please, for me, and for you, more importantly, that z times z bar equals r squared is a circle, because z times z bar just comes to x squared plus y squared. Good? You getting that? Great. Now let's, yeah, it's a circle, centre of the origin, and radius r. Right? Now let's do this beastie. This is a little bit harder to see, but it's just as easy when you work it out. Okay, and I want you to recognise this one very well, because that's a favourite of the exam setters. all right? Now that looks like a dreadful mess, doesn't it? I've put them all sausage machined out. So that's Z is X plus IY, C is A plus IB, Z bar is X minus IY, and C bar is A minus IB, right? Goodness, what have I done? I've unleashed a monster. However, don't worry, let's get the ducklings all sorted out, get the reals together with the imaginaries, and look how much easier it becomes. Oh, it's almost miraculous. So, what have we got here? Now, look, see this? X minus A is the leading term, and you've got, goodness, look at this, plus I times Y minus B, and minus I times Y minus B. Look at that. That's how it works out. Now, that's a difference of two squares. That's why I'm aware of the difference of two square. See, that's why I'm getting excited, because that's really just takes all the heat out of it, and there's no sting in its tail anymore. It's just basically the first term all squared minus the second term all squared. Now, that I squared that's going to come out of there is going to turn into a plus 1, isn't it? Minus I squared is going to get us plus 1. So you can see now what's going to happen. Yes, ain't it grand? It's a circle. It's a circle. Thanks, Mr. Box. It's a circle. And it's got a centre of A and B, which is the complex number C. C equals A plus IB, and the radius is R, right? Yes. Hurrah for R. Now, this beast up here, this is just so obvious. Look, real part of Z is X, and the imaginary part of Z is Y, so this is just saying X squared plus Y squared equals R squared. But I put it in because I want you to recognise it, and I've just put it down here as just for the sake of putting it in, because that's the other form. So they're all the forms of the circles that I've ever seen. There's this one, there's this one, there's this one, there's the one we've already dealt with, like the modulus of Z minus A equals 4 or something. Okay, that's a circle for sure, and the one that I just did on the previous screen, where that coefficient wasn't equal to 1 thing. That's it. That's all the circles that I can possibly pull out of the hat for you. Now, get ready. We're going to do an analysis question. Oh, all right. Yes, Mr. Computer. That's a circle, centre 0, radius R. Thank you so much. Hurrah. Now, or huzzah. This is an analysis question. Now, I want you to have a go at this question before I actually do it, so that you'll have had a go at it, okay? Because it's a typical exam analysis question, very, very typical, okay? So, please pause the video at any time you feel confident and have a go at it before I basically let the cat out of the bag, okay? So, what do we got? We've got S is a set of complex numbers Z, such that the distance from Z from the point 1 is less than or equal to 1, right? Okay, T, what's T? Well, gracious me, T. That doesn't fill us with glee. We're saying that right, so we're looking at T as a set of numbers Z such that the distance of Z from the point 1 is greater than or equal to the distance of Z from the point 1/2 plus root 3 over 2i. Remember, you've got to put a bracket around here, okay? Z minus, open bracket, 1/2 plus root 3 over 2i, close bracket. So, right, that is set of points Z so that the distance of Z from 1 is greater than or equal to the distance of Z from the point 1/2 plus root 3 over 2i. So there's the coefficient of this is 1, so still we're looking at a perpendicular bisector situation, but this greater than thing turns that into a region. Okay, I've given too much away now. I'll stop. Okay, so find and sketch the set S on the Cartesian plane. That's the first bit. Okay, on the B is on the same set of axes, sketch T. Same set of axes, sketch T. Third bit is sketch S and T, where both have to apply at the same time, showing all relevant points, right? And the last bit, which is the king hit, is find the area represented by S and T, expressing your answer in exact form. And the king hit is going to be our king hit on it, basically, not it on us. So, yes. Now, please have a go, pause the video, have a go, and look, you just might surprise yourself with what you can do. But this is a very typical exam question, and therefore you're going to have to think about it. Think about it, okay? Particularly D. It's probably might give you a bit of a run for your money, but that's what they always do in the exams. They hit you with a king hit at, on the last part, but we're going to king hit them, okay, before they king hit us. So pause, have a go, come back. See you soon. Go and get a nice cup of tea too. All right, you're back. Right, A for us today. That's an easy one, right? That's going to be the inside of a circle, including the circle itself. Circle and interior. Centre is going to be 1 and 0, yes, and the radius is going to be 1. So we have to do this. Find and sketch the set S on the Cartesian plane. Right, that's what we're going to do. There it is. Now it's the inside of that circle, isn't it? And the circle itself. Yeah, that's right. That's what it is. Okay? Good. You agree with me? Great. Now, okay, what are we got to do with... we've got to find... That's part A. We've done it. Part B now, we've got to find T. Now, that's a bit tricky, so let's just take it easy with that. Okay, so I think we'll find the perpendicular bisector of the line joining those 2 points first. That is 1, 0, and the point where Z is a half plus root 3 over 2I. Yeah, so what are we dealing with? These points here, 1, 0 and a half, root 3 over 2, yeah? We can do that pretty easily. We'll do it geometrically if you don't mind. Right, so let's draw a picture. Yeah, right, there's the 2 points. Now let's, call them A, B. That's our little diagram. We've got to get the perpendicular bisector of that red line AB. Well, let's do the midpoint first. Midpoint, it's the average of the points. So that's x. For x, it's going to be a half plus 1 over 2. For y, it's going to be root 3 over 2 plus 0 all over 2, or the other way around, it doesn't matter. And we're going to get that. Yes, 1.5 over 2 is 3 over 2 over 2, which is 3 over 4. Root 3 over 2 over 2 is root 3 over 4. Yes, I'm convinced. Are you happy with that? Good. And I've just marked it in with the very faintest of dots, just to get my bearings here. Now I'm going to do, what have I got to do now? Gradients, don't I? So the gradient of AB is y2 minus y1, which looks right, over x2 minus x1, which also looks right. So I'd say that's going to be, seeing the 2's are going to cancel out, we're going to get minus a half on the bottom line though. So therefore it's going to be minus root 3, I'd say. Do you agree? Yeah, good, excellent. So therefore, of the normal, we want plus 1 over root 3 because we know that m1 times m2 equals minus 1 for perpendicular lines. So therefore, I've put it in. I'm using y minus y1 equals m times x minus x1 format there. So here, look at this. We've got y minus, that's the midpoint of y. That's the gradient, and that's the midpoint for x, okay? So that comes to, seeing I was running out of room, forgive me, but I just did a little bit of mental arithmetic, and not mental arithmetic, I did it on my piece of paper, and I got y equals 1 over root 3 times x. That's pretty interesting, isn't it, Mr. Box? Oh, no, it's not Mr. Box, because that's just an intermediate result. That's Mr. Box's first cousin. Right, so there you go. Now, what am I going to do now? I've got the equation, haven't I? So, oh yes, we're going to go over the page to show you what's going on, because that's only where that's only the perpendicular bisector. We've got to deal with the greater than or equal to bit now. Okay, I've got to show you that, how that works. So there's the line, y equals 1 over root 3x. There's the midpoint. There's everything drawn in beautifully for you. Now, so what am I trying to find? So let's just put this down on paper or on screen for you. Y equals 1 over root 3x is the locus of where z minus 1 equals z, okay, minus a half minus root 3 over 2i. In other words, the distance of z from 1, which is here, there, is equal to the distance of z from here. That's what we're saying. And that perpendicular bisector line shows you every single possible place where those distances are equal back to A and B with straight line of sight lines. Yeah? Can you see it? Right. But that's not what we're looking for. We're looking for, we want the points where what have I written there? 1 equals. Just forget the 1 equals. We're looking for the points where the distance of z from 1 is greater than or equal to the distance of z from a half plus root 3 over 2I. Now, if you think about that, guys, just try this line here. Just try this line here, right? Now, at this point here, the distance of z from 1 is exactly equal to the distance of z from this one, the point A, yeah? Okay, so if the distance of z from 1 is got to be greater than or equal to, you're saying, okay, the distance, let's try that line bit there. The distance of, if z was that point there, the distance back to 1 would be greater than or equal to the distance back to the point half and root 3 over 2, wouldn't it? Of course it would. So basically what I'm saying is if it's greater than or equal to, it means it's further from 1, from B, than it is from A. So can you see which region we're looking at here? We're looking at, the distance, if the distance of z from 1, 0 is greater than the distance from a half and root 3 over 2, okay? Now, which section do you think? Well, here's the answer. Then you basically want the region above the line, okay? And including the line itself. Now, you'll notice I just performed a little bit of magic and got rid of that mistake because I couldn't stand it, so it's nice and fixed now. So therefore, okay, what we want the locus required is everywhere on the line and above the line. Now let's draw it in. There it is. Okay, now can you see that? See how you work it out from just straight, normal, common or garden logic, you know? Common or garden logic, okay? That's how you do it. So don't freak out, just, you know, the answer is never very far away. That's not that hard when you think about it, you know, and draw a diagram so that you can get your head straight, okay? All right, now, so let's have a look at this. We're going to draw the whole thing on here. We have to draw it on the same diagram, remember? We have to draw T on the same diagram, right? So here it comes. This is part B of the question done. So we've done it now, okay? Written in blue for me and you can see that, right? This is region T. So it's the line plus everywhere above the line, all right? Good, show. You happy enough? All right, let's go. Now, what have we got to do now? Oh, we're just finishing this off. We've got to work out the intersection points. If we're going to show two regions joining up, we've got to find the intersection points, okay? So therefore, that's the first equation, and there's the second equation, which we're interested in here to get the intersection points from, okay? Alright, so we're just doing straight simultaneous equation solving here, and we're getting that. Oh, hello Mr. Thumbs Up, how are you? I think he's pretty good. So, otherwise he wouldn't have his thumbs up. So therefore we've got this now. Oh yes, I see. Yeah, okay. Substitute for y from 1. Yeah, that's all right. That's just x over root 3 all squared. Substituted instead of having y there, okay? So that's equation 2. All right, so therefore we're getting that. Now we're going to solve this thing for x. Oh, that's nice. The ones went. Good. We need all the help we can get. Oh, no, we don't. We're going well. Now, what have we got here? I think we can take out a common factor of x out of here. 2x. Goodness. It's getting ambitious. So that works well. So x could be, by the null factor law, x would be 0, or x would be 3 over 2, with just a little bit of skullduggery algebraically wise. We get that. So that looks like the two intersection points. We've got to work out the y values though. If x is 0, y would be 0, of course, and if x is 3 over 2, y would be 3 over 2 times, 1 over root 3 times x, which gets us root 3 over 2. That's pretty interesting, isn't it? So therefore, I've put them in for you. Now we've got everything complete. That's one intersection point of the line with the circle, and this one up here is the other intersection point of the line with the circle. Good. That's great. Okay? Now, let's go on. I think we're going to do part C. We have to sketch S and T showing all relevant points. Well, I think we've actually done it. It's just that we've just got to make it a bit clearer. We're actually talking about this little slice of the circle here, aren't we? They're the two that apply at the same time, aren't they? And we've got the intersection points. We did them in anticipation. Right? Good. So let's just do that. So there's where we got to. That's the point. That's the point there. That's S and T for you and me. Right? Happy? Good. Now, what's the last part? Okay, find the area represented by S and T. Expressing your answer in exact form. Now, this is going to require a little bit of ingenuity, not freaking out, remembering that the answer is never very far away. They're asking us for this area here, and all we've got is a couple of intersection points. Now, come on, guys, look. What you do here is you just start thinking, well, this can't be very hard. I'm just a Year 12 student. It can't be impossible. So let's just see what I already know. Well, I know what we know. You could probably draw a line from here up to here, and that then looks like you've got a sector of a circle, and you've got a triangle there as well. And if I worked out the area of the sector, that's the pizza slice, right around there, and I subtracted the area of the triangle from it, then I'd have the area that I need. But is it possible to do that? That's the point. How can I do that? Well, just fasten your seatbelts and have a look. I've drawn this, it all gets a bit microscopic, but I've drawn that little triangle there. Now, what have I drawn? So I've got a triangle here, goes from C to E to F, right? And this looks like D. Now, C, D, E, F, right? Now, if you think about this, look, this point, the centre of the circle was at 1. This point here had an x-coordinate of 3 over 2, same as this coordinate here, this point of intersection. So that's got an x-coordinate there of 3 over 2 because it's a vertical line, same x-coordinate. Therefore, that length is a half, isn't it? Convinced? Yep, good. Now, what about the vertical? Okay, so what are we doing in the vertical here? We've got this point here is root 3 over 2 y-coordinate. This point here has 0 y-coordinate. Therefore, the length, that vertical line there, must be root 3 over 2 units long. Now, ladies and gentlemen, look at this. This angle here, what do you think? What do you think this angle might be? What do you think for you and me? It's the angle whose tangent is root 3 over 2 over a half. The 2's are going to cancel out, and that will just get us root 3 over 1. Now, what is the angle that has a tangent of root 3 over 1? Yes, yes, yes. 60 degrees. A very familiar angle for you and me. So I'm starting to show you what's going on here. Okay, now I'll just continue on with the documentation here. So I'm considering that little triangle that we were just looking at. So the angle CEF, which is, the angle CEF is this angle in here, which I was just explaining to you, is a 60-degree angle because it's the angle whose tangent is root 3 over 2 over a half, which is the angle whose tangent is root 3, which is pi on 3. Pi on 3 radians. Therefore, ladies and gentlemen, what is this angle? This has got to be the rest. Take away pi on 3 from pi, being a straight line, you get 2 pi on 3. So if that's 120 degrees or 2 pi on 3, now I'm armed with some very, very vital information. Okay? And what's the radius of this circle? Yeah, it's 1. Therefore, that length there from D to E is 1, and from E to C is also 1. goodness, it's all falling into our lap, isn't it? So therefore, we're saying that the angle CED is 2 pi on 3, like I just said, and therefore the area of the sector, the pizza slice, come on, how do you do that? It's the area of the circle times the fraction that the angle that makes that sector is of a full revolution. So it's pi times 1 squared times 2 pi over 3 over the full 2 pi. Yes, isn't it? Yes, it is. So look at that. What's happening? What am I doing? I'm getting so excited. Oh, it's pi over 3 square units, isn't it? That's the area of the sector. Now, if we can just get the area of that triangle, which is an absolute piece of cake now, we can subtract the area of that triangle from the full sector, and we get S and T for you and me. So come on. Wasn't that beautiful? You have to admit. Come on. Yes, yes, good. Glad to hear you admitting it. So therefore the area of triangle DEC for you and me, now that's the area of a triangle is half AB sine C, if you know. Do you remember that formula? Well, I hope you do, because you're going to need it in the exams. So it's a half of this length, which is 1, times this length, which is 1, times sine of the angle between them, which is a 2 pi on 3 angle. And what's the sine of 2 pi on 3? It's the same as the sine of pi on 3, isn't it? And what's the sine of pi on 3? It's root 3 on 2. Of course I heard you say that. So now we've got the area of triangle DEC. So how do you get S and T? Yes, you take that away from the area of the sector, and what do you get? You get the final knockout punch. We've king hit them. They didn't do it to us. So therefore, what it is, it's the area of the sector, which was pi on 3, minus the area of the triangle, which is 3 pi on root 3 on 4, and that's good enough, guys. Mr. Box, thank you, Mr. Box. Now, how'd you like it? Yeah, did you get it out? Well, jolly good upon you if you didn't. If you did, and if you didn't, that's all right. You'll get used to them as you practice them. And you're a star, and yes, we'll all go far. Hurrah and huzzah! And I'll see you next time. That was a very long session, but I'll see you next time for more excitement. See you. Bye.